Let's get started again. Got a lot of ground to cover here. So here is my solution to the program. We've talked about this at length. I call this the single program multiple data, or SPMD design pattern. And if you spend a lot of time with me or the courses I teach, I talk a lot about design patterns. Design patterns are the fundamental algorithmic kernel you capture in your head. And I want you to think about them as you learn parallel programming, because once you master the patterns, then you can carry them from one language to the next. And it really, whether you use OpenMP or CUDA or OpenACC or SYCL or MPI or TBB, I don't care. You change the spelling of constructs, you just use the same patterns. So SPMD is what happens when you run the same program on each processing element. Each processing element takes care of a different chunk of the problem, and you split it up by using the rank, which is an ID ranging from 0 to the number of processors -1. So you split up the work based on the rank and based on the number of processors. If you write code with MPI, which we will talk about tomorrow, this is the pattern you use, SPMD. It is without doubt the most commonly used pattern in all of parallel programming. And I like to start with it when I teach OpenMP because it works really well in OpenMP. And we're not going to have a chance to go into it at all, but in an advanced OpenMP programming course, I show you how by using the SPMD program, I can deal with a lot of non-uniform memory architecture issues. So actually in professional quality OpenMP programs, even though I'm going to show you much easier ways to solve the problem we just did, you sometimes need to fall back on this pattern. So it's really good to know. All right, I need to, though, briefly digress. Remember, this is an introduction to parallel programming using OpenMP. There's a concept in parallel programming we have to talk about. So I want you to think about your program. It consists of a collection of independent tasks. And remember, when I say the word task, I mean very specifically a sequence of instructions and the data environment those instructions need to execute. So imagine I have n independent tasks. So I'm going to load some data and I'm going to run those independent tasks, and then I'm going to consume the results. So to a first order of approximation, the time to run that is the time to do the load, n times the number of the time for a task, plus the time to consume. And this is just a crude, simple model. Let's not get into not all tasks are going to run the same amount of time. Yeah. For this sake, assume they do. I put an average run time for a task there. And so if I'm running in parallel, it's very simple arithmetic. Time for parallel equals, well, the time for load, I didn't parallelize, but the number of tasks I did. So my runtime there is n over the number of processing elements times the tasks. Okay, so that's going to be my parallel runtime. So ideally, what I'm kind of hoping is that my runtime is directly proportional to 1 over the number of processing elements. If I double the number of processing elements, my program is going to run in half the time. That's kind of what we dream about. So I can talk about the speed up, which is the ratio of the time of my sequential program running on one processor divided by the time of my parallel program running on P processors. That's the speed up. And so if everything is ideal, everything really, real ideal, then I would have that the speed up equals the number of processors. Okay, we call that perfect linear speed up. And in my dreams, when I have a really good dream at night that makes me just feel all warm and cuddly all over, I'm dreaming of getting perfect linear speed up out of my parallel programmers. Typically, of course, you're not always that lucky. But at any rate, that's great. I'm going to mention it briefly because sometimes you get this wacky situation where the speed up is greater than the number of processors. We call that superlinear speed up. And that usually happens with cache effects. As I'm adding more and more processors, I'm splitting up the problem into smaller and smaller and smaller chunks. And it can happen that all of a sudden a chunk fits in the cache. And as you know, a CPU running out of the cache is really fast. So I can get this weird situation. Now, this is very important. I hear idiots sometimes talk about we can beat Amdahl's law. It's like, no, it's a law. You can't beat Amdahl's law. So I'm going to walk you through what Amdahl's law is. So we can take a look at what I did in the last couple slides, and you can think that the time for a parallel program equals the serial fraction of the code plus the parallel fraction over P times the time from a sequential fraction. I love talking to physicists because you'd be amazed is when you move away from the physicists and physical sciences, people look at an equation like this and it really throws them for a loop. So yeah, physicists rock. So if my serial fraction is alpha and the parallel fraction is 1 minus alpha, I can plug it into this equation, crank some simple algebra, and what I get is that the speed up is this expression, 1 over alpha plus 1 minus alpha over P. And we can say that, okay, as P goes to infinity. So imagine I can throw just an astronomical huge number of processing elements. What Amdahl's law says is the maximum possible speed up you can ever see is 1 over the serial fraction. And let me be really clear, that serial fraction is everything you don't improve by adding processors. So it's 1 over your overheads. Now this is critically important because you hear people talk about exascale computing, and okay, Intel is building for Argonne National Labs as a customer, an exascale machine. My company is a big believer in all over exascale computing. I'm an official exaskeptic, always have been, even though I work on exascale computing, right? And the thing is, how many applications have a serial fraction below 1%? The answer is not a lot. How many parallel programs have a serial fraction under 0.001%? Almost none. Very, 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 very few. Getting a serial fraction below 100, below 1%, below 1,000th of 1%, this is Herculean effort. The number of programs that have, overheads that are less than 1 in a million, which is what you're talking about for exascale, is ridiculous, ridiculously small. So you're going to build an exascale machine and spend vast, vast sums of national wealth for a handful of programs that can actually use it. It's dumb. But, the US needs to wave the flag and say, we got the fastest computer in the world. And so we got to do it. But, this is how we sell high performance computing, is convincing the funders that we need 1,000-fold improvement every decade. And the next improvement is the exascale, okay? And as soon as we finish that, we'll want zetascale. No, because of Amdahl's law, for tightly coupled parallel programs, you're talking much smaller numbers. And you don't get around Amdahl's law. Amdahl's law is, there's no way around it. And therefore, when you're talking extreme scalability, you have to be insanely fanatical about parallelizing everything, about overheads. I mean, it's amazing the lengths you have to go if you really care about extreme scalability. Fortunately, most of the time, speed ups, if I can run on 32, 64, 128 cores, 200 cores, yeah, that's good enough. Most science is done on these modest sized machines. And so it shows up, though, not just on the extreme scale. This is just showing for different values of the parallel fraction, how even for small number of nodes, it starts to show up. And this equation is just, this plot just comes from plugging in those numbers into the speed up equation I showed you earlier. So that's Amdahl's law. And so now you see the meaning of my stupid introductory slide, that, I know how to turn math into lines on a speed up plot, because when you do work on a parallel program and you're going to announce your parallel program performance, you always need to show a speed up plot. And if you're an honest parallel programmer, and I hope all of you are honest parallel programmers, you want to find this point where it breaks off, okay? Because at some point in any given algorithm, you're going to hit a point where overheads grow. Synchronization overhead, which we'll talk about soon, grows. You know, you didn't use parallel I/O, so the I/O overhead comes to dominate. So as a good parallel programmer, you always want to get this speed up plot, and you always want to see where that break off from perfect linear speed up occurs. And then you know that, okay, for this program, if I'm always going to run it less than that break off, this algorithm is good enough. But if I know that I need to run it for a value of p that's beyond that break off, then I have to go back and rework the algorithm because I need to get more done. All right, so obviously there's a lot more I could talk about there, but it's just, I want you to know the language of performance. When I throw words around like speed up, you know what I mean. Okay, so number of questions. How do I control the number of threads? And remember, I told you that OMP set num threads changes the default number of threads. And there's a lot of detail on this slide that for right now, because we're a little behind where I wanted us to be, I won't go into, but you know, you'll have these slides, you can study them. The real point of this slide is if I were delivering a production program, I would not want my user to have to recompile every single time they wanted to change the number of threads. That just doesn't work. So what you do is you have an environment variable, OMP num threads, and you set it that way. And so in your program, you don't set the number of threads. You know, you just don't set the number of threads. Oh, I added all sorts of stuff here. It may not run at all. But I get rid of that statement altogether. And I make num bigger than I'm ever going to want it. On this machine, let's say 16. Okay, so that's my max. All right, and now I go through and, well, yeah. It's going to work. Good. So then I go export OMP num threads equals 1. And so now when I run it, I'm running on 1 thread. Of course, I didn't have it print that many threads. But now I can go through and I can change it to 2. So by doing this, run it again. You know, hey, it went a little bit faster. So you can see I can do this again and again. And I can collect the data and build my speed up plot. So you can see, wow, 1 thread, go to 2. By 3 threads, I'm down to that. And then, you know, because it's my operating system thinks there's 4 cores. So let's complete this. So as you can see that by the time I get to the 4 cores, I'm getting a speed up on the order of 2. Now that's important because this is the operating system thinks there's 4 cores. On my little laptop, there's physically only 2 cores. So, you know, this is, oh, I look at this and go, yeah, that's good speed up. Hey, this is cool. All right. So that's how we actually work with the number of threads, is we don't set it in the program, we do it in the environment variable. Now, we're not going to do this exercise now because I want to pick up a little time. But I would then have you do what I just did, playing around with OOP num threads and running it and getting your speed up plot. And on the laptop where I used to make these slides, this is the result I got. And the speed up kind of sucks. You know, just I would like to do better than that. What's going on? And here's what's going on. And this is a very important slide. So hang in there with me. When you think about running on a microprocessor, this is true GPUs, this is true CPUs, but we hit it more with CPUs. You have a cache hierarchy. Cache hierarchy in a GPU is relatively simple. On a CPU, it's fairly complicated. But let's just think about it. You need the caches because the memory, DRAM, is much, much, much slower than the CPU. So I need some really, really fast static random access memory, SRAM, right up near the core. And so those are my caches. Now I use that array, that sum array. Let's stick with the 4 core case. And the size of the cache line is such that those arrays, some 0, some 1, some 2, some 3, are all going to be sitting in the same cache line. Now, that's done by default because typically, remember, if you read array element 0, chances are you're going to want to read array element 1. So we designed the cache hierarchy assuming that. But think about as we were using it in the Pi program, all right? So hardware thread 0 goes and says, hey, I'm going to do an update to some 0, all right? Then along comes hardware thread 2, who's on a different core, and it goes and says, okay, I'm ready to do the update in my copy of sum. Yeah, let's go. And the cache hierarchy is going to come back, the cache protocol, the cache coherence protocol, is going to come back and say, no, 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 your cache line's dirty. You got to wait. Okay, so you wait, and then it'll slough over from core 0, the cache line, to core 1. And now core 1 has the cache line, and it's going to do the write. Meanwhile, hardware thread 0 is ready to write its next iteration, and it goes to do that, and the cache coherence protocol comes back and says, no, 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 stop. Your cache line's dirty because someone else is now using it. Okay, oh, wait. And so what you have going on is even though each of those array elements are truly distinct, there is no true sharing. It is a race-free program, as we wrote that Pi program. It is a race-free program, is correct. There's no sharing, but the cache lines happen to be shared. The cache coherence protocol makes sure you'll get the right answer. But from a performance point of view, what I'm measuring is the time to keep bouncing that cache line back and forth, back and forth, back and forth, back and forth. This is called false sharing. It's a concept that's important to know. And it's just, you have to think about how are the arrays that I'm working with laid out in the cache hierarchy. And if they happen to all be sitting in the same line inside a tight memory access loop, maybe I need to spread them out. And how would I spread them out? Here's a dirty little trick. It's ugly, but it works. I'll put a second dimension. Look at my sum array. Now, instead of just num threads, I'm now going to add a second dimension pad. And I will pick that based on the size, the L1 cache of the processor I'm using. I will pick it so it's the size of a cache line. So now what I have done, now inside my loop, if I go back down and look at the loop, sum of ID of 0. So I don't care which element, I'm not using that value, but I'm just using it to force each new value of some ID to be on a different cache line. It's called padding your array, and it works. It gets rid of the false sharing. And now all of a sudden, yay, I get really nice speed ups going from 1 to 4 threads just by that one simple trick. That's ugly. That is ugly. If I move to a machine with a different size cache line, I have to change the padding. The thing is about programming is the person writes the code and the code lives longer than they do. So imagine some poor software engineer comes along and looks at this code and goes, why the hell did you put a second array there? So, I mean, this is just bad on so many levels. There's got to be a better way. And there is. And to go there, we have to talk about synchronization. Okay. Oh, gosh. I'm going to say briefly what I mean by cache line, but this is a conversation I'll stick around during your lunch break, and we can go into that in more detail. But it's, as I said, a cache is memory that's very, very fast, that sits close to the CPU, and it's broken down into blocks. The size of those blocks is called a cache line. And when you do a memory access, it all happens at the level of a cache line. And the idea is because since you're almost always going to want the successive values, you don't get a single value out of memory. You get the whole block equal to the size of a cache line. That's getting into architecture details, but we can talk about that during the break later if you'd like. Okay. So synchronization. It is important to think about the fact that the threads are concurrent, meaning they're unordered. There are times you want to impose an order constraint. That's what synchronization is. Precisely, that's it. Synchronization defines an order constraint between threads so that you can say this thing happens before that thing. I could give a 4-hour lecture on synchronization. It can get that complicated. It really can. Fortunately for you, as scientific programming people, if you were going to be writing an operating system, you would need that 4-hour lecture. But since you're not writing operating systems, you're splitting up loops and doing linear algebra, and you don't have to get into the ugly, ugly details. We can just deal the high level stuff. And most of what you need are two synchronization constructs: a critical section and a barrier. So we're going to talk about those right now. So, what a critical section does is it defines a piece of code that can only be executed by one thread at a time. We call it mutual exclusion. So here's an example. I have a piece of code. I create a bunch of threads, pragma OMP parallel. This all should look familiar. This is the SPMD pattern, right? So we get our ID, we get the number of threads, we call a big old messy function. And then after that big old messy function's done, I'm going to accumulate the results. And for whatever reason, I want the update of the variable res to happen with mutual exclusion so they don't get in each other's way. I have a function called consume that someone wrote, okay? And it may have side effects, and I want to make sure those side effects are protected. So I want to make that execution of that function, consume, taking the argument b, I want to make that protected as well. So only one thread at a time runs it. So pragma OMP critical does that. And I can put brackets so I can have multiple statements in it. Remember, in C, a block of code is equal to one statement or multiple statements between brackets. So I can make a critical section as big as I want. But remember, critical section says only one thread at a time runs the code. It serializes that piece of code. It's as non-parallel as it gets. So be careful what you put in a critical section. But this gives me mutual exclusion. The other synchronization construct is a barrier. And this one's really handy. So what it says is this defines a point in the program where every thread has to arrive before any can continue. Now there's a barrier at the end of any parallel region. I've even used the word barrier with you before, right? All the threads have to reach that closing bracket at the end of the parallel region before that initial thread can continue. So we call that an implied barrier. So there's a barrier at the end of the parallel region. But what if you want to stick barriers at other points in your program? And here's a case where you would use it. Now the barrier is a standalone pragma. It's the first one of these we've seen here. It doesn't have a block of code associated with it. It's a standalone pragma that does an action inside the program. So here we go. I have an array R and BR, and I set my number of threads at 8. So now I have my pragma OMP parallel. And at this point, those next 3 lines, ID equals OMP, get num thread, end threads, ID equals 0 is num threads. That should look tremendously familiar to you right now, right? Now I do a calculation in parallel. So this is standard SPMD style, right? I'm going to assign its value to ID of R. I'm going to run a big ugly calculation. But notice the next statement where I update the array BR. It uses ARR. So I want to make sure before I start this next big ugly calculation that everyone has finished their part of the ARR array. Okay, so I don't want anyone to start their calculations on BR, until everyone has finished R. So that's where I would put a pragma barrier in there. So this guarantees everyone's done with R. Okay, now I can compute on R. And so you can see why we would use it. It's when I need to tell people that, whoa, calm down. We need to make sure you can use this array safely. Stop. All right, that's what we would do. So we're actually, because we're running out of time. No, I'm not going to do that. I can't skip this exercise. Okay. Save your Pi program you did originally in a separate file. And then using a copy of it, what I want you to do, and I'm going to only give you 10 minutes to do this, because if you understand everything I just said, that should be enough time. What I want you to do is don't use an array for sum. Give each thread its own partial sum value to sum into. But now use a critical section so that I can safely accumulate into the partial sum. All right. Basically, we're going to get rid of that trick of using an array to give a safe sum. And instead, we're going to use an individual accumulator for partial sum. And then we will use the critical section to accumulate into the final sum. Go for it. Okay, we're about the 6-minute mark. If you're stuck, ask a question. How's it going? Anyone have this done yet? Oh, didn't know the mic picked that up. I thought I muted. I've had important meetings at Intel, high-level meetings, where I pick up my guitar thinking I'm muted and start playing. It's the danger of a home office.
Just tell them it helps you think.
That's right. It's actually fascinating to me how many serious musicians I find in the computer science community. I've often wondered if there's something about the brain of hardcore programmers that overlaps with serious musicians, serious music. I don't know. It'd be a fun study to do. Look across academic disciplines, and do you find correlations between which discipline you pursue and what your attitude is towards making music? 2 more minutes and I'll get started again. You know, I wonder for those of you who are the organizers of this event, there's a lecture that I sometimes give as part of the parallel computing intro, is what every scientific programmer should know about architecture, where you describe caches. You know, most people program their whole life and never know about how important the translation look-aside buffer is. You know, what does it mean to have an L1, an L2, an L3? Can you thrash your instruction cache? What the hell is an instruction cache? You know, there's just a handful of these architectural issues, and it's only a, you know, it's only a 30-minute segment. It doesn't have to be a long, you know, because it's for scientific programmers, not computer scientists. But there's just a few things. I feel the same way about floating point arithmetic. It amazes me how many people do scientific programming, scientific computing without really, I mean, they use the word floating point, they know about float, but do they really know the IEEE 754 standard and how it shows up in how it shows up in different algorithms? You know, people don't get formal education in numerical analysis anymore. And there's a few things from numerical analysis people probably should know. So, anyway, I should probably get going again. So let's go. And I'm sorry if you're feeling rushed. What we're going to do here is we're going to get, you know, I'm going to hit the time point end I was given. And what I'm going to urge you to do is between now and the time we get together, catch up on any exercises you didn't finish. And I am going to give you a homework problem. We'll finish with an exercise, but do them between now and we get together tomorrow. So it's okay if you're a little bit behind. So, oh, get back on the screen. Okay. So here's my solution to the problem. Remember, we had this where if, you know, we took the scalar sum in our original program and we promoted it to an array. That's a common trick. Promote the sum of scalar to an array to create a way to give each thread its own piece to work on. And so what I did is I put that back to a scalar. So now it's just sum again. And I declare it inside the parallel region. So now each thread has its own copy of sum. And now it does its operation on its own copy of sum. So there's not likely that well, those will not be on the same cache line. So I'm okay. Then when I get to the end of the loop, I combine it into the global copy of pi inside the critical section. Okay, that's all it takes. It's pretty cool, isn't it? No array, no false sharing. It's really nice. And if you see, if I look, I'm now running the same as that padded case. So that gives me evidence that yes, indeed, false sharing was my problem. And by using that critical section, I got rid of it. So yay, that was successful. Now, a common solution, if we walked around, if we were doing this face to face and we walked around the room and looked at everyone's solution, a subset of you did this. You put the critical section inside the loop. It makes sense. That's a perfectly logical thing to do. All right. No one's saying, oh, you're dumb. No. But think about what that does. That just serialized the loop. The fact that the loop is, I call this a tight loop. There's not a lot of work each loop iteration. There's just what, 2, 3, 4 adds and a multiply. I mean, I'm sorry, 3 adds, a multiply, and a division. That's all there is in the loop. Okay, so each thread's just flying through its loops. And so if you put that pragma OMP critical in the middle of that, all the threads are really just spending their time waiting for their turn to do that, to be able to execute that next statement. So this would be abysmal performance. So what I urge you to do is, between now and tonight, when I think you really need to just play with this, try it. See what happens if you put that inside. All right. So we've now talked about how to create threads. We've talked about the concept of synchronization, putting an order constraint. Right there, you can do a huge amount of hardcore multi-threaded programming. I can't stress enough. You could walk away from this course now and you would be able to start doing serious professional level multi-threaded programming. And if you think about it, we haven't covered that much new stuff. So I think that's pretty cool. That's really pretty awesome. But we got to talk about this next one, parallel loops. Creating a bunch of threads and then splitting up the work between those threads. We call that work sharing. Sharing the work between the threads. And since so much of what we care about is invested around loops, it would be really nice if when I have a loop, I want to split up between threads, if I could just tell it, do that. I don't care about block or cyclic or how you do it. Just take this loop and give a different piece of it to each thread. That's what Pragma OMP4 does. So if we assume here that the loop body, which is calling a function called neat stuff, another meeting I'm missing today, yay. If you think about a loop that's just calling that function neat stuff, and if we assume that function neat stuff is completely independent from one thread to the next, I now have a parallel program here, Pragma OMP4. So I always have to create the threads, Pragma OMP parallel. The only way to get multiple threads is that parallel region. So I create the threads and then I go and say, split up that for loop between the threads. Done. Now, I told you earlier that if you know OpenMP for C, you know OpenMP for Fortran, because the construct names are all the same. There's one exception. The loop in Fortran, since I think some of you must be Fortran programmers, I don't know if you're aware of it. When God did the simulations for creation, she used Fortran 77. So I like to point out that Fortran 77 is God's language. And in Fortran, the loop construct is not for, it's do. So if you're using OpenMP in Fortran, it would be Pragma OMP do, but then you need Pragma OMP and do. All right. And if I don't give it further information on how to, we're going to talk in a moment, but if I give it no further information for how to split up those loop iterations, it's going to do it whatever way it wants. I'm saying I don't care, just do it. I'll show you later how to, if you care, to change that. Now, at the end of a work sharing construct, of which a for loop is one, there's a few other work sharing constructs. There's an implied barrier. So let's be really clear how this will execute. Pragma OMP parallel creates threads. Pragma OMP4 figures out how it's going to split up those loop iterations, and then it splits them up. When all the threads are done, they're going to wait. There's a barrier at the end of that for statement. And we do that because our goal with OpenMP was to make the common stuff safe. So in many cases, if you do a computation inside a loop, the statements following the loop are going to use the results of the loop. So you kind of want a barrier at the end of the loop. So we do that by default. Now there's another thing we do for you. Imagine if the loop control index, I, was a shared variable. What would that do for loop controlling? I mean, think about the loop execution. You know, I equals 0, and I'm going to increment I. Well, if I'm incrementing I halfway through while someone else is starting the next iteration, what value do they read? It's a data race. It's a mess. So we could conceive of absolutely no reason you would ever want the loop control index to be shared. So for the loop that's impacted by the Pragma OMP4, and only that loop, we make its loop control index private. So each thread will have its own copy of I. So this right here is a correct OpenMP program for splitting up that loop. Now, this is a point where we're going to review and think about what we've done before. So I have a sequential code that's going to do an array addition and accumulate into A. So at the top is the one-line statement of that. Now, if we do it with the SPMD style, with everything from OpenMP we've used up to this point, I could write this code this way. Okay, I start equals that, I end equals that, and I think I have a bug there I have to fix. There we go. You know, if by the last thread of that group, I'm going to set the value at end. You know, so this is the way you've been seeing us do this all along. Or I could do Pragma OMP parallel Pragma OMP4. Which of those would you rather write? Which of those is the most error prone? There's no doubt this is a lot easier. And most people working with OpenMP, this is all they learn. Pragma OMP parallel, Pragma OMP4, done. Okay. And there's a question about the definition of a cache line. As I said, when we get to the lunch break, I will stay and I will answer these architecture questions. But this is a topic of computer architecture. All right, now, there are times you want to tell the compiler how you want it to split up that loop. And so we have the ability for you to add a schedule clause. So I would have Pragma OMP for schedule. And then in schedule, you should have the type of schedule, dynamic or static, and then chunk. And I'm going to describe what all this means. Let's start with static. So I can have Pragma OMP4 schedule static. And what that's going to do is if I don't have chunk, because it's an optional parameter, what it's going to do is it's going to create one block of loop iterations per thread and then assign it to each thread. Okay? So and they will be contiguous loop iterations. So we'll get one chunk per thread. So that's pretty much what this case here is doing. All right? This is doing the equivalent of Pragma OMP schedule static with no chunk size. But if I give it a chunk size, and I will often do this maybe to help block my iterations around the size of the memory hierarchy, sizes in the memory hierarchy. So I may have Pragma OMP static 10 or 16. You know, you play around and you find something. So there are cases where you're organizing your data around the cache hierarchy where you want a chunk size that's smaller. No problem. What it will do is we'll break the loop iterations up into blocks of size chunk and then deal those out like a deck of cards. That's cyclic distribution. So one thread gets the first chunk, the next thread gets the second chunk, and you just then, when you're done with your chunk, you get the chunk incremented by the number of threads. So you go through exactly like that cyclic distribution, but instead of dealing out individual loop iterations, you're dealing out blocks of size chunk. And all of the logic for supporting the static schedule can be done at compile time. So it has very, very low overhead at runtime. So that's what we really like about static. Now, there are programs you're going to do, however, you're going to work with, where static doesn't work, where the distribution of the work is completely data dependent, and it might change in the course of the computation. You know, for me personally, this comes up in molecular dynamics, where I'm doing, you know, the Coulomb potential and various other higher order dynamic potentials between the various atoms in a molecule. And what do molecules do? They flop all over. So the neighborhood of any given atom changes as a function of time. So any fixed distribution of chunks, if I'm chunking my loop is over atoms, any given fixed distribution is guaranteed to be wrong at some point later in the computation. So this is where it's like, no, I want to dynamically assign those loop iterations. How do I do that? So dynamic, what you do is it's as if you put the loop iterations in a queue, and you give each thread the first iteration to work with. And then when it's done, it goes back to the queue and says, okay, give me the next piece of work you want me to do. So now chunk says, just like static, okay, well, you break it up into a number of iterations, a block of iterations of size chunk. So if I go pragma OMP4 scheduled dynamic chunk, let's say the chunk 10, now I'm saying that, okay, each thread you get 10 iterations. When you're done, you get 10 more iterations. When you're done, you get 10 more iterations until you're all done. The default chunk size for static is that you give one chunk per thread. The default chunk size for dynamic is 1. So that's how they work. But remember, anytime you have a shared data structure, like the queue for managing the distribution of work, I'm having to use synchronization logic to make it safe. So there's a lot of overhead in dynamic. And so you want to be darn sure that if you're using dynamic, the work really requires it. And I'll tell you, in practice, what we do is we try them, we just play with them. Don't try and reason it out too much. You just play and try different ones. Now, here's a little simplification that we use a lot. There's a very, very common pattern where I'm going to create a team of threads just to work on one loop. So I have to go pragma OMP parallel and then pragma OMP 4. That's kind of clunky. Why can't I combine them? And yes, indeed, I can. These two cases, the code on the right, the code on the left, they are completely, strictly equivalent. Pragma OMP parallel 4. And as I said, the world's majority of, the hundreds of thousands, if not millions of programmers out there who use OpenMP, to most of them, OpenMP is go through your code, find the compute intensive loops, put a pragma OMP parallel 4 on the loops. Your program's going to break, go back to those loops and figure out where you have a conflict, a loop carry dependency or a data race. Fix that conflict, you're done. That's, for most people, that's OpenMP programming. I don't start there because then what happens is they're ignorant of threads. So I always like to start with the bare bones SPMD so that you understand, wait a minute, there are threads. Oh, there are variables local to a thread. Oh, wait, there's variables shared across threads. I want you to deeply understand that before we show you this easy thing. Pragma OMP parallel 4. Now, there's one other situation though. Oh, wait, no. I'm gonna talk about this. So I go through and I look at my program and I look at my loop, and let's say I recognize that this loop right here, for I equals 0, I less than max, element of A equals big function call. And then I increment J and go back and again. Okay, I now have a loop carry dependence between J. So you have to go through and you have to look at where are the loop carry dependencies and then shift your logic to get rid of the loop carry dependencies. You want to make those loops so the iterations are independent and so they can execute in any order. In fact, I'll tell you a real common debugging trick is what if I start the loop I equals max, I greater than 0, I minus minus. In other words, run through the loop in reverse. If your serial program loop gives you the same answer running forward and running in reverse, you probably have an independent loop. And you may go and say, wait a minute, man, this is easy. You can just tell by inspection. Yeah. Imagine your loop is 10 pages of source code of text. And inside that 10 pages of text, you're calling, 50 different functions. I'm sorry, you can't always get there by inspection. So, these tricks of testing it out are actually really useful sometimes. So you want your loops so that you get the right answer, even if they run forward or run in reverse. You want to make sure there are no loop carry dependencies. And here's a common situation removing a loop carry dependence. I have j plus equals 2. Well, I can compute that with a function of I. So, j equals 5, and then I increment it by 2 for each count. So if I go j equals 5 plus 2 times I plus 1, now I don't have a loop carry dependence. Oh, Vincent asked an important question that I want to make sure you understand. Remember, in the C programming language, a block is one statement or a block of statements. As far as that pragma OMP parallel 4 is concerned, there's one statement. It's the for statement. So that's the block. I don't need the curly braces. I can put them there. I could put a break, an open bracket, and a closed bracket, but there's only one statement. So that's why I don't need the brackets on the pragma OMP parallel 4. That one's important. Thank you. Glad you asked that. All right. Now, here's an important case. And this is the last concept of new concepts we're going to cover today, because we're going to end with the next big exercise that you get to do tonight. Because you like homework, right? Yeah, of course. You're all having so much fun. You're going to spend tonight just writing OpenMP code, right? So look at this code block here. Simple as can be. I'm going to accumulate into a variable, average, AVE, av. And then when I'm done, I'm going to divide by the number of loop iterations and get the average value of that array. So what the computation here is so easy and brain dead obvious. That's a loop carry dependence. How do I get rid of that? Oh man, am I going to have to go and do all that ugliness with, like we did with sum, create an array for A, give each thread its own private copy of A. That's really ugly. Okay, this pattern of accumulating into a value is so common that every parallel programming language that I consider worth using builds it in. It's called a reduction. So I'm reducing a bunch of values, like from an array or from something else. I'm reducing them into a single value. It's called a reduction. And this is so common. Any kind of programming environment that's worth using has it built in. And so does OpenMP. So OpenMP has a reduction clause. So I'd have pragma, OMP, parallel, for, reduction. So let me explain what reduction does. And this explanation is going to seem kind of involved compared to what it's brain dead obvious what I'm doing, right? Yeah, well, it can get tricky. Let me explain. So the syntax is reduction, then you give an operator, then a colon, then a list. And that's a list of variables. Those variables are the reduction variable. So, I can have multiple variables in my reduction clause. So inside the parallel region, or the work sharing construct, I can put this on a parallel or I can put it on a work sharing construct. So inside the construct, the compiler will give you a local copy of each variable in the list. Local meaning it's private to each thread. So now every thread will have its own copy of a variable called av. It will initialize that variable based on the identity of the operator. And we all know that the identity of plus is 0. If it was multiply, if my op was multiply instead of plus, what would the variable equal? And now I would look around everyone and I'd wave my arms and everyone would yell out 1, just to make sure people understand what the word identity means, right? So you're going to create a private copy of the variable for each and every thread, initialize it to the identity, and then you're going to do the operations inside the construct into that local copy. When you hit the barrier at the end of that construct, you will combine all those local copies using that operator. All right, so inside the loop over an average, every thread's going to have its own private copy of average. It'll do its share of that accumulation. And then when you get to that curly bracket at the end of the loop, we have an implied barrier. Remember I mentioned that? And then I will now use that operator plus to combine them all. Then when I am done, phew, come on, aren't we done yet? No. Then when I am done with that, I will use that operator to combine it with the global value, the original value. Okay, what do I mean? We have to have the variable shared to start with. It has to exist after the construct. I initialize it to 0. So now I'm going to do all that work inside the loop. I'm going to do the independent values of AVE. I'm going to combine them to have a global value of AVE. I will then add that to the value of AVE, which in this case I said is 0. Okay? So if this value, keep in mind, it's 0. If we're doing the average, it should be 0, but I could have it some other value. It's a well-defined operation still, is the point I'm trying to make. Now, there's a delicious subtlety here. It's amazing the different ways you can use this reduction. Because notice in the definition I gave you, at no point did I say anything about it using the reduction operator inside the loop. Inside the loop, I don't care what you do with AVE. I could care less, okay? It's called AVE, but it doesn't have to be an average. So I can pass it to functions, I can multiply it, I can, use it in a sign and assign to it. I can do crazy stuff to it. I don't care. That operator on the reduction clause just tells me how am I going to initialize it, and when I hit that barrier, how am I going to combine it? That's all it does. So it's actually much, much more powerful than the simple case I'm showing you here. And the question, can I use reduction on multiple variables? Yes, that list could be a comma-separated list of variables with multiple operators. No, it's the one operator. Now, I could have multiple reduction clauses, though. So in one program, I can have one variable being reduced with plus. I can have another variable, different variable, being reduced with the multiply. So, you can have multiple. Now, if you dig into the spec, there's a lot more we can say about reduction operators. But in the common core, in common usage, the reduction's used with plus. That's like so overwhelmingly where it's used. Every now and then you see a multiply and a min and a max. Do this operation and I only want to keep the maximum. But there are other cases, and the log and this isn't a complete list. You go into the spec and you can see the complete list. But I only do this shortened list because, as I said, when I look at programs, I never see anything that's not on the slide in front of you. And overwhelmingly, all I see is plus or multiply. So that's for the operator. Now, we aren't going to cover it at all, but you have the ability to create a user-defined reduction. This is important because if you're using C++ and I have objects and classes and all that C++y stuff, you need the ability to do reductions over C++ objects. And I just want to tell you, we're not going to talk about it because it's getting into advanced stuff, but I just want to tell you that yes, indeed, there are user-defined reductions defined in OpenMP. As scientific programmers solving partial differential equations, we pretty much don't go there. But yes, indeed, there are plenty of programs where you do. Another thing I haven't gone through is the variable in that array, the variable in the reduction it can be an array as well. I can reduce into arrays. A little bit of extra syntax, but I don't want to go into that now, but it is there. So now, your exercise tonight, or this afternoon, this evening, whenever, is I want you to go back to your original serial pi program, make a copy of it, and I want you to parallelize it just with the things you see on this screen, a parallel and a for, and a reduction. All right? Your goal is to see what is the minimum number of changes you can make to the source code, the original source code, to create a parallel program. How many lines? Can you do it with 2 lines, 5 lines, 4 lines? Your goal is to get that line count down as low as possible. And this is important philosophically, because when we first sat down to create OpenMP, way back in 1996, yes, indeed, I am really old because I was there. Our goal was to make it so that you could minimally transform a serial Fortran program into a parallel program. That was our goal. And so it was very important to us that you made minimal changes. And remember, in the Fortran case, your directives are comments. The compiler doesn't change syntax based on a comment. If the compiler doesn't recognize the comment, it will skip it. So we'll have no semantic impact. Same thing with a pragma. If the compiler doesn't recognize the pragma, it skips it. So our goal is that you could write a program that would work with an OpenMP and a non-OpenMP program, so that you made minimal syntactic changes to the program. So that's what you're playing with here. So I'm going to leave you with this. I'm going to use our remaining 7 minutes before your lunch break to answer questions. But when we get together tomorrow, I want to talk about your solution to this exercise. And I also urge you, catch up. If there's exercises you didn't quite finish, catch up and finish them. I will check this chat here, this Discord chat throughout the day. So remember, to me, it's only a little after 10 o'clock. So I'll be around, for a long time, the next 8 hours. So ask your questions here. I will check in and help you out. And I'm hoping by the time we get together tomorrow, all of you will have finished all the exercises. And I can't stress enough, play. Try to break things. Try different things. Try different schedules. Measure different speed ups. I mean, you learn by playing around with these concepts. And it would be really great if you show up tomorrow and you've fully played your way through these concepts. All right, that's it.